We will start with chapter 5 on Thursday, and then probably, if there is time, a review for the quiz on Tuesday. All right? The quiz on Tuesday will just be chapter 4. So, pressure, states of matter, density, buoyancy, the Archimedes principle, and what we do today, which is the Pascal principle and the Bernoulli principle. It's all now about fluids. So I want to do a few problems today. The weekly problems have already been uploaded, and they are all about pressure. There's one or two problems about the Pascal principle, and there are a few problems of buoyancy. Now, there are plenty of applications for buoyancy. We can have objects floating in water or any other fluid, liquid, right? We can have the balloon problem that we talked about last class, and I will try to do it using numbers today, so you can see at least how that pans out using Newton's laws. And then in some way or form that will help you to reinforce some ideas. So the Archimedes principle is telling you that the buoyancy, right, due to a liquid is equal to the weight of the fluid displaced. So whatever fluid has been displaced, the weight of it is equal to the buoyancy. And if you remember, there were some equations that we did last class. We had the density that we label it like that. In the book they use D. The problem with D is that we also use D for other variables, like distance. So I normally use the rho, okay? So that is the Greek notation for density. You can just have that, which is mass over volume. But if you rearrange this equation, you get that density times the volume of any object is equal to the mass. And furthermore, if we multiply by gravity, density times the volume of the object times gravity is equal to the weight of the object. So if I know the volume of the liquid displaced, how can I find the volume of the displaced water? Well, if you remember what I showed you last class, actually, why don't I show you to you now again? And then we can do that problem. So, there, right? When you introduce an object, like you see there, part of the liquid is going to go to the next glass. If you measure the weight, that missing weight, which we call apparent weight, is equal to the real weight minus the buoyancy, the scale reading. All right? So that's apparent weight. So when you're in water and you feel like you have less weight, there you are. Which is the reason why the astronauts, you probably know, they train for the walkthroughs they do in space by the absence of gravity, in swimming pools, specialized technical, it's not like any swimming pool, right? But they are in some way or form, they can emulate the absence of gravity due to the buoyancy, right? So they can actually see how they can walk and how they can test their equipment, all right? So that's important. And that will be the source of at least one theoretical question in the quiz to explain the graph, to explain apparent weight, or in a problem, maybe something like what I'm going to do right now on the board. On the board, I have sort of like what you see there, but there's no, the weight is not hanging. There are no readings. So you see the whiteboard. There. There is a mass floating on water. So the idea with the problem is to find, so let's find how much of the object is in water. We can find in terms of the volume of the object, the percentage of the object inside. Right? So I will say that this whole object has volume V, and inside the water is just X. And I can solve the problem, because if this is floating, so let's put here sort of like equilibrium, right? If I say that the object is floating, then I can say that the weight of the object is equal to the buoyancy. That's what happens when an object floats in water. Okay? And that's good, because now I can use the equation for weight, which is here. So the weight of the object is the density of the object times the volume of the object, which is V, times gravity. And that's equal to, okay, what was the equation for buoyancy? Buoyancy is a force is equal to the density of the liquid or the fluid times gravity times the volume submerged. The weight only acts here, right? If we do forces diagram, there is a weight mg, and there is also the buoyancy. The buoyancy for that object will be the density of the liquid times how much of the object is inside water, x. I'm using x. It's not the length of this, all right? I'm just saying that x is the volume inside water. So x times gravity. Gravity cancels. So what's the density of the object? Now it says that it's wood, and that's the density of wood. So 160 times the volume of the object is equal to, so it's water. The density of water, remember, the density of water is 1,000 kilograms per meter cube. There. I want to find X. So, I get this. Right? I divide by 1,000 on both sides. And then I can cancel the zero. Look what I get, guys. I get 0.16 times the volume is equal to X. Or, you can say that 16% of the volume is X. That means that the object is only submerged 16% of it. Almost a sixth part. So that's how you solve a problem of buoyancy. When you have an object floating in water in this case. The equations are in the slides, but I would strongly suggest to have a small equation sheet. All right? I will see if I can get you guys one, but the main focus is not to do many problems, right? We want to do a few here and there, but we want to understand the concept. All right? So they might be giving in the exam, I'm giving you guys the equations for in the exam, but as I said, the main idea is that you understand, in this case, Archimedes' principle. Okay? So that's an application of Archimedes' principle there. All right? Let's take a look at the balloon. We were doing that last class before we finished, right? We're talking about a helium balloon immersed in air. So, as you can see here, the key value for these problems is the density. If you know the density of the fluid and the density of the object in this case, then you can tell the buoyancy and the weight, and they both are forces. So it's all recorded, but there you are. Okay. So let's take a look at the problem with the balloon, and then we can finish with Pascal principle and Bernoulli, and then do a few problems, and pretty much that's it, guys. I will probably do a problem on pressure. Let's leave that in there. Buoyancy. Let's draw a balloon, but now I'm going to give you values. So conveniently, even though we know that's always the case, but a balloon with radius 6 centimeters. Is that right? No, that's not a lot, right? Let's say 20 centimeters. Yeah. That's the balloon. And like that. But when I say that, that's negligible, okay? The string is negligible. So there is helium here. And there is air. Air.
Professor,
Yes.
sorry, I cannot see the board.
Oh.
I can't see anything.
That's right there, right?
Yeah, much better.
Yeah, that was the line. I forgot about that. Okay, so we have the balloon, and there is air. We want to find the buoyancy now. Now, Remember that in the slides, there was a table there. So this will also be given. So let's write it down anyway. The density of air and the density of helium. The density of air in the table is 1.29 kilograms. You know something? Be careful with the values. You are looking for mass density. And the units also help, right? 1.29 kilograms per meter cube. And the density of helium is 0.18. It's very tiny in comparison. Very tiny. So why do I need a density? Because with the density of air, I can find the buoyancy. Now I have the radius. And we're going to assume it's a sphere. It's a balloon, right? So I guess you also will need for this problem the volume of the sphere, which is 4/3 pi r cubed. You need that. And that's it, right? Because gravity, you know what's the value of gravity? Is 9.8 meters per second squared. And you have the volume. Now, the balloon is immersed in air, right? I mean, we are here right now in the air, so we are surrounded by air. So the volume that we use for buoyancy is the volume of the total object, the volume of the balloon. And the volume to get the weight of the object, the weight of helium per se, is the volume of the balloon as well. Because you remember, this one, like the discussion about states of matter is relevant, right? A gas is a state of matter that gets the shape of the container, right? It covers the container that holds it. In that case, the gas will take the shape of the balloon. So the helium inside gets expanded all over the volume of the balloon. So it makes sense to use the volume of helium the same as the volume of the balloon. Okay? So let's find and let's see the difference. Okay? So let's find the buoyancy first. As you know, the buoyancy acts like this, right? That's the force of buoyancy. And the weight of the balloon, just like that. That's the weight. So the buoyancy okay, the buoyancy is the density of the liquid, sorry, of the fluid, which is air, times gravity times the volume of the balloon inside air. So you know what you do? You put here 4/3 pi. The radius is 20 centimeters. Be careful, it has to be meters. So times 0.2 cube. And obviously, now you will need the use of the calculator, right? So as you can see in the equation there, we will use 1.29 times 9.8 times the volume of the balloon point yeah 0.424. So I get 0.424 newtons. And what's the weight? The weight of helium, or the weight of the balloon, will be the density of helium times gravity times the same volume. And clearly, it will be less. It will be less. And it will be less because you are dealing now with a much smaller density, right? That's 0.18. Gravity doesn't change, so times 9.8 times 4 times pi times the volume. You get 0.06. It's very tiny. So the weight is just 0.06 newtons. So you can see, right? This 0.4 to 0.06. So that force difference makes the balloon go up. Now, that will be the only thing I will ask you. You can get something else from this. If you are clear with the concept of density and mass, you can get the mass of helium. If you think about it, the mass of helium is that the weight of helium divided by 9.8. And why do we need a mass of helium? Because force equals to mass of acceleration. I can find the acceleration of the balloon going upwards. But that value will be not very trustworthy because we are neglecting the mass of the balloon itself, the plastic container, right? A balloon is sometimes made of plastic or whatever type of paper, right? So, plastic, right? So obviously, we cannot neglect that, all right? There are problems that, don't worry, not at this level, but there are problems where you can actually compute those type of things. Here I just wanted to show you that there is a case. This is a case where the buoyancy is not the same as the weight. That's why the balloon goes up. All right. Yeah. So let's show you a few of the slides. The good thing is that it's all recorded. So let's see. So we have the Archimedes principle here, and that's a table I was talking to you guys about, mass density. We don't really use weight density. Specific gravity also we don't really, all right? And we normally use, as you have seen already, kilograms per meter cubed. So that's why I was talking to you guys about this in pounds, and that's the balloon there, all right? Actually, look, that's a nice problem because that is with two balloons. So you have the weight of the balloon and the weight of the balloon with hydrogen. So they are giving you the net force in both the balloon full of hydrogen and the balloon full of helium, right? So clearly, for the hydrogen balloon, there is more force going up. Okay, that's because of the density. All right, the density of the balloon, of the element, in this case hydrogen. So we can repeat the same calculations. Let's take a look actually. What's the density of hydrogen? Oh, So that's interesting. The density of hydrogen is even lower. It's exactly half the density of helium. Look here. So that's why there will be less weight, more force going up. The buoyancy doesn't change because the buoyancy depends on air, and both balloons are in air. That's why the force on the balloon full of hydrogen is larger. Let's try to think about these guys. Acting on a boat in water at rest is equal to the weight of the water displaced by the boat. What's the answer for that? What's the force acting on a boat floating on water? Anybody?
Buoyant force?
Buoyant force. Exactly. Buoyancy. Job. One balloon is filled with pure water and a second filled with antifreeze. What does each balloon do after being released by a scuba diver beneath the surface? So you are beneath the water, all right? One is filled with pure water, and a second one is filled. Okay, you know what you have to do for that case, guys? We have to take a look at the densities. Let's see if they're in here. There it is. So if you want to know what happens with any substance inside water, iron, wood, or in this case the antifreeze and water, right? Remember that the density of seawater is way different than the density of water and obviously different than the density of antifreeze. So let's try to think about that, right? Let's start thinking about water and seawater. The density of seawater is actually greater. Look at this, or here. So there is more density of seawater. That means that if you have a bubble inside the water, when you put the seawater, right? When you put the water, the seawater exerts more buoyancy than the weight of the water. Does that make sense? Does that make sense? Look at this number, right? The weight of water depends on the density of water and the volume, right? The buoyancy depends on the density of the seawater. So there is more buoyancy. So then the seawater will go up. What about the antifreeze? There it is. The antifreeze has a density of 1100. So the weight of the antifreeze inside the bubble, because of the density of the antifreeze, will be more than the buoyancy. So it will sink. Okay, that's how you answer these questions. The water will rise and the one with the antifreeze will sink. Make sense? That's another question I can ask you as well in the quiz. Why do some objects rise or fall in water? All right, it has to do with the density and the buoyancy. All right, just remember that. As a person climbs into a rowboat, it must sink lower in water so that think about when you guys go into a rowboat. You probably feel like you are losing equilibrium, right? And it actually sinks a little bit when you step on it. The net force on the boat remains zero. Yes. So that's important. The net force does remain zero. Because if it wasn't zero, it will either sink or it will go up. You make the boat sink a little bit, but then it reaches equilibrium, right? So the net force on the boat remains zero. True. All right, yes. It displaces more water, consequently increasing the buoyancy. So let's suppose the boat is in water and is floating due to the buoyancy, right? So there is a force. The weight of the displaced water is equal to the buoyancy. So the buoyancy has to go up because you have displaced more water. So it displaces more water, consequently the buoyant force on it. Yes, true. The bottom is deeper in the water. Well, now you know that the answer is all of the above. But let's look at this one. Its bottom is deeper than the water where the higher pressure causes the rise. Okay, so remember that the pressure depends on the height, right? So if you're going underwater, you will experience more pressure and you can feel it in your ears. All right? Now, I want to show you guys today a problem where we do pressure between two fluids. That's part of that homework that you guys are going to see today. Not homework, like the assignment, wiki problems, right? The buoyant force on a hydrogen-filled balloon is larger than that on a helium-filled balloon. The buoyant force, the buoyancy, is greater in helium than in hydrogen? No. Why? Because the buoyancy depends on what? On the fluid, not on the elements. And what's the fluid? Air. Right? If helium and balloon are right now, if I'm holding right here, let's suppose this is let's suppose I have here helium. It's not helium, of course, but let's maximize this. Let's suppose I have helium here and hydrogen here, right? The buoyancy is the same. It's just that the hydrogen will rise faster because the weight of hydrogen is less. The weight of helium is more because helium has a higher density. Okay, that's the key. The buoyancy doesn't depend on this. It depends on the density of the fluid. Sorry guys, let's see. I have a call here. Let's see if this is wait guys, let me see. No, it's not that. It's not what I'm thinking. Okay, that's weird. There's a meeting today in Union, that's why. Pascal. Okay, so now we can talk about Pascal principle. And that's one of the last important concepts. The Pascal principle, guys, in fact, I was discussing this with a friend that works in hydraulics. It's universal. And the Pascal principle, you use it in toothpaste, you use it in your brakes, right? In your braking system. You use it in when you ride a bike and you make it stop. You use it in hydraulics. When you want to lift an object, right? Basically, what it says is that in an enclosed, isolated device, where there is a fluid, water, oil, whatever, the pressure is the same. the pressure that you apply is transmitted. It goes through the liquid, through the fluid, evenly. Let me show you an example of what I'm talking about. The best example for this is this here. Oh, here. There. There. I think they still use that in mechanics, in like when you go to the mechanic, when you want to lift a car. That is a very common device where you have a piston. So here you have a piston. And normally you have a device that you push. And then you push several times and you can lift a 3 to 4 ton car. In this case, I gave them 2 ton. 2 ton is 2,000 kilograms, quite a lot. What is the key feature? That there is a fluid connecting both the piston and where the car is suspended, right? So the idea is that while you push the piston, you are applying some pressure, force divided by area. There. That same goes to this side. But remember, right? If the pressure is the same, the pressure here is transmitted here. Force divided by area is equal to force divided by area. But if the area is larger here, the force is larger because they are proportional, right? Force and area. If one goes up, the other one goes up. So the idea is the same as with your brakes. So sometimes people wonder, right? Especially with today's cars, right? When you press the brake slightly, you can make a car stop very quickly, right? Unless you are driving a truck. But even for a truck, right? You can be driving a 5, 6 ton, 7 tons car, truck, and then you just press the brake and you can make it stop. How come? By just exerting a little bit of force, you are making this big truck stop because of Pascal principle. And that's what they use in hydraulics when they want to lift heavy weights, right? For example, in the harbors, when we have imports, right? We wanna move those big metallic containers, right? So the machinery uses the Pascal principle. So normally the difference of areas has to be huge. The bigger the difference, the larger the force that you will be transmitting. Okay, so it's good that I found this. This was an exam I gave a few years ago. Not for this course, but the same topic. So obviously, toothpaste, right? When you have it and you press it, then the toothpaste will come. And the thing is, right, if you press it very hard, then and the toothpaste is full, then you have a lot of it. That's why you have to be very careful, right? And that explains why, as you consume more and more of that cream, it's harder. You have to press more force. There it is, guys. And the equation is there. It's a very easy equation. All right. You will have an example of that in a quiz, an exam for sure. And I will show you a problem. It can be like the problem I just showed you, by the way. I'll give you the areas, I tell you how much force I'm applying, and I ask you about how much force will be transmitted to the other side. And then you have this, right? So there it is, guys. That's your brake system. It's more complex. It's not as simple as just one area and two areas, right? There's a whole bunch of wheel cylinders and brake pads. What's a brake pad, right? That's why brake pads need to be changed every, I believe, 3-4 years. Because by applying force so much, or by doing heavy brakes, that gets wasted little by little. So the brake pads are the one that they push. You see here, look. There. So by applying the force on the pedal and by making this go toward the disc rotor to stop the tire, this is the tire here, then the brake pads get used too much. Okay, very nice, right? It's nice when you guys can see an application in real life, and that's one of those. Okay, this is a problem. All right, let's do an exercise on this. Okay, so I will give you the same system I showed you in that exam, and the typical question will be having a piston and a large piston where there is a big mass in one of them. Okay, and I will ask you to find the force transmitted. Okay, so you can have a device like this. Like that. Like that. And here you have a piston with a large area. And here you have a small piston where you will be applying a force. Alright? So let's apply a force here. F. The areas will be given in meters squared. So let's say the area here is 0.0025 meter squared, and the area here will be 0.0625. And the fluid normally is, it doesn't matter, but normally for this type of devices is oil, all right? Because it has a very low viscosity. But don't worry about that for now. It's just a fluid. It's isolated, enclosed, no leaks, all right? And okay, so they want to know how much force you need to apply to be able to lift a car. So there here is going to be a car. All right, and the car has a mass of 17,500 newtons. It takes more time to draw than do it, than solving it. You know why? Because this is, as I said, the Pascal principle. And the Pascal principle tells you this, that let's call this F1, A1. This will be, right, F2 and A2. So the Pascal principle tells you that F1 over A1, so the pressure there is equal to the pressure here, F2 over A2. And if I solve this, I get F1 over 0.0025 equals to, what's the force? The force is the weight of the car, and they give you that, 17,500. Divided by 0.0625. If I do my math, so again, calculator, 0.0025 times 17,500 divided by 0.0625. I only need to apply a force of 700 newtons. So my force is of 700 newtons. Just to put it into perspective, 700 newtons in terms of mass is approximately the mass of a person. The mass of a person average is between 70 and 75 kilograms, which is approximately 700 newtons, right? Between 700 and 750 newtons. So basically you can just stand there and you will be able to do that. So that's Pascal principle, okay? And as I mentioned in the weekly problems, okay, there is a problem like that, where they give you a hydraulic machine, all right? So we've done everything that needs to be covered in there. The only thing that I want to cover right now is, I believe we can go into the last section of this. Let me see what we have. So that's a problem there. That's a solution. Bernoulli's principle. Okay. Now, the math, honestly, guys, you don't have to worry about the math here. Just about this, the equation of continuity. Okay, and that's how we're gonna finish with this. Bernoulli's principle is okay. So far, for Pascal principle and buoyancy, we have discussed about static fluids. So, for example, this, right? You see there's a fluid. Oh, no, you don't see it. But if you're in a pool and you see the water still, that's a static fluid, there's no motion. But in your pipe system at home, right, in the draining system or whatever, there is a steady flow, as it says there, a steady flow of liquid. The best example is, let's say you have a container of water and you have a big hose connecting the container of water from the basement of your house to the second floor. So the machine, or a machine, sorry, is going to try to pump water. Another example would be this. Back in the day, this would be common. Nowadays, I think, well, maybe it still happens. Let's suppose that you run out of fuel in the middle of the boat. So I have seen people doing this. They have a hose and they connect the hose basically, or they ask for help to another car that has a full tank, right? Or maybe not full, but they have fuel to spare. And they use a hose and they bump some of the oil, some of the fuel. You have to be careful how you do that though. They bump it and they pass it towards the car that has an empty tank, right? So that's using the principle, that's using the Bernoulli principle. How come? Because when you pump, it's like when you are using a straw. You are applying a pressure difference. And that's the key on the Bernoulli's principle. As it says there, the pressure is lower where the fluid is flowing faster. So the pressure difference can stop a flow of fluid. Like that. So that's the basic principle of fluids inside pipes and how they can go from one pipe to another pipe and back to another pipe. The difference that you measure is in the pressure. The Bernoulli's principle is far more complex because you do have pressure difference due to heights, but you also have pressure difference due to the speed. There is a term that we use in fluids, which is called the caudal. The caudal, in Spanish caudal, it's the way we measure the flow of a river. Is the volume divided by time. So in the case of a river, right, when we want to measure the caudal of the river, we compute how much of that can be contained in a certain, we call it dique. I don't know how you call that in English, but it's a device that you use to get water, all right? And normally they use it to clean it and then they can, you know, pass it on houses. But how do we measure that? By knowing the caudal, right? In English it's the same, but it's written with a Q. So that is constant. When you have pipes and you have pressure difference and different cross-sectional areas that you see here, the pressure changes. Look at this, right here. The pressure is changing. The areas are changing. The velocity is changing, but not the caudal. That's the caudal. And that is basically the equation of continuity. The caudal in one zone of the fluid or pipe is identical to the caudal on the other side of the pipe. You know what's another way to understand that? Is this. Let's suppose it's not very windy, but you are in a normal day of autumn where there can be all of a sudden some sort of wind. Not very strong like winter, but so. You are on the street and you don't feel it so much. As soon as you enter an alley, the speed normally is higher. It's larger. There is more, you feel it more, you feel more intensity of the air hitting you. You know why? The explanation is in front of you right now. Because when you're on the street, the area of the street normally is large, right? There's a road and houses and but when you enter an alley, the area shrinks. So let's take a look at this. Look at the equation here. When the area is bigger, the velocity is lower. When the area is lower, the area is bigger. Because these are inverse proportional. So remember, air is also a fluid. So that works. Right? Bernoulli's principle works for fluids. Normally we apply for water, that's true. But you can explain what I just told you about the air in an alley because of the equation of continuity. Right? Which is why now that people want to be outdoors, as soon as it becomes windy and you have enclosed, for example, right? I've seen restaurants that they have alleys. Here in Union, around Elizabeth, there is a few of them. And that's good. I mean, they were able to place tables, right? But even on summer, when the temperature dropped a little bit, you know, to 70 sometimes, and there was wind, you could feel more wind in those alleys. And the food would get colder faster, right? But the thing is that that's because of that, Bernoulli's principle, right? The air will flow faster. All right? Well, there is a problem here, but the idea is more about how you can use it. For example, in this case, right? Atomizers, perfume bottles, they use Bernoulli's principle. When you squeeze, well, that you don't use anymore, right? But back in the day, when you squeeze the bulb, the air will move through the horizontal tube and it will move faster due to the pressure difference. So you lower the pressure and then the velocity as it comes out will be greater. All right, you are playing with the pressure. The same idea as a straw. You can get water drinking a soda or water using a straw because of pressure difference. All right, and the pressure difference is the key for Bernoulli's principle. I didn't show you the equation though. There is an equation that relates them. Don't worry about that. That's not the goal of this course. All right, it's just the continuity equation, guys. So then we have a few things here. All right, and then we have the summary, guys. So chapter 4 is very conceptual, but there are a few problems. All right, remember that we started with the states of matter, and we include plasma. We talk about compounds, molecules, the elements as well. We talk about pressure, mass density. We did talk about weight density, but as you probably have figured, mass density is the key parameter, all right, and pressure. We introduce liquids and gases as fluids, okay? And then from that, we introduce the law of fluid pressure, and we prove that pressure is what? Density times gravity times height. And we introduce Archimedes' principle, buoyancy, Pascal principle, and Bernoulli's principle. Okay? So I think it's a good way to stop today, guys. By the way, there it is. I had it already there. So I want you guys to have that. Okay? We are going to be using SI units. Don't worry about that. And any value will be given to you guys on the quiz. Now, as you probably have figured as well, quizzes are not that bad. Tests are a bit more challenging because you may get more problems, but also because you have more chapters. Next chapter is chapter 5, which is temperature and thermodynamics. Again, very conceptual, but with a few problems here and there. And then we have waves. Those 3 chapters will be on exam 2, which should be in November before Thanksgiving. All right? And then we will finish the course with electricity and magnetism. And then those topics will be in exam 3, and then the whole course in the final exam. All right? So far I think you guys are doing very good. I saw your grades, and I don't think you have to worry about passing. I think you guys are going to pass, but I want you to learn and make sure that if you ever have to apply some of this, at least you know, right? And you are learning some things in here, right? The Pascal principle, things that you probably didn't think about, that you apply every day, there you are, right? There are many physics in daily life. Anyway, I hope you guys enjoyed the class. I will see you guys on Thursday for maybe I do a couple of problems on this, and then I can introduce chapter 5. The quiz on chapter 4, guys, Tuesday next week, okay? Do you have any questions?
Yes, Professor, that you mean the quiz for this chapter that will be next week?
Yeah, on Tuesday.
Okay. Okay. Thank you so much. Yeah.
Yeah, so you can study for it. Okay. And then finish the homework, guys. I changed all the due dates for the homeworks. All right? So now they have been extended almost a week and a half. So finish chapter 4, and then chapter 5 is already open. We're going to start that next class. All right, guys. Have a nice rest of your day.
Thank you. You too. Bye-bye.
Thank you.